Hello again and welcome back to this intermediate JavaScript tutorial series. I'm John, and in this episode we will be building off what we learned about the call stack and try and get a complete understanding of the event loop. Let's get going. And as always, all the material that we cover in this episode will be available on my GitHub, link in the description. Feel free to leave a star if you found it useful. In this episode, we're covering number 5, event loop, and we'll be opening up this event loop.html. So the first thing we're greeted with is this really good image that's visualizing the event loop. One thing that you should note is if you watched last episode, the first thing we should see is that a portion of this actually contains what we learned in last episode. We see the heap, where information is stored, and the stack, which handles what's going on right now. On top of that, we see these web APIs and this callback queue. These are the next building blocks that are needed to complete this event loop. You can probably already understand why it's called the event loop. So what are they? The queue is similar to the stack, only it's first in, first out. Instead of frames, we have messages, and messages are sent from the queue to the stack. A message is run to completion before the next is sent to the stack. So if we look up here, an on-click element would have been set by a web API. In this case, it's pertaining to the DOM, or the document object model. And when that was clicked, the web API is what would have sent that event to the queue. Now, seeing as onClick was sent to the queue before onload, as soon as the stack is run to completion, this onClick will be set onto the stack. Just to go over it again, the main difference between this queue and the stack is onClick came in first and is going to be the first one sent to the stack, whereas on the stack, it's last in, first out. So foo's called first, Baz is calling bar, and now when bar's run to completion, it's popped off the stack. Then Baz will be completed, popped off the stack, and finally, foo will be completed. Now, something to note that's not in that image, that in the browser specifically, there are actually two main queues that we're dealing with. The callback queue, which we see, and the render queue. While the callback queue sends a message to the stack as soon as it's allowed, the render queue attempts to run a new render every 16.6 milliseconds, which is at 60 frames per second. And so that's a slight caveat to what I said before. When this stack is cleared, if the render queue has waited too long, it will actually take precedent over this onClick message. It'll re-render the page, and then this onClick message will be sent to the stack. Web APIs, as I said before, include things like set timeout, which aren't actually a part of the JavaScript core language. JavaScript engines and browsers make certain APIs accessible, such as that set timeout, set interval, and request animation frame, as well as things like DOM events, so click events, and AJAX calls. Web APIs have the ability to add new messages to the callback queue, and that's exactly what we see in this image. It's the web API that's giving you this onClick and onload. So for a good visual example, I'm linking to this page. You can see it's built by Philip Roberts from And Yet. Code is on GitHub. He gives a good talk where he kind of goes in depth on a lot of what I talked about last episode and this episode. So if you're interested in this material, I would definitely recommend watching this video. Now, what this essentially does is it takes the JavaScript code, slows it down, and it shows you the order that events happen on the call stack via web APIs and the callback queue. And he even has this toggle for simulate renders, which we might look at in a bit. But first, I'm going to take some code that I wrote to use as an example. Paste it in, and let's reformat this real quick. So what I'm doing here now is essentially a primitive version of what we see in the event loop image. I'm having foo call Baz, Baz call bar, and each one of these is logging out foo and then Baz and bar. But what I'm also doing is creating this set timeout for 0 seconds, which runs this function, immediate timeout function, where we're console logging. This is from the web API. Now what we see here is currently the main function. Everything here is going to run to completion before any events can actually happen. Therefore, despite this set timeout being for 0 milliseconds, foo will run first, which is going to trigger Baz and then bar. And it won't be until all of those finish that we get the log from this immediate timeout function. So let's watch it. Save and run. We'll see that set timeout is triggered. Now foo is running, Baz, and then bar. and those are going to finish one at a time. And then that callback is called, where it's logging and finishing. Finally, I'm going to simulate renders. And this is what I was talking about earlier with the render queue. This runs incrementally, and this is displaying when the window would need to be repainted. So let's run our example again and see if we run into any problems. Well, we set that timeout and repainted, but now while foo, bar, and baz are running, our render queue is actually stuck waiting. When those finish, it renders again before calling this immediate timeout function. When that's finished, we're back to our standard rendering schedule. So I hope that made sense from a conceptual and visual standpoint. But what's a practical example of a time where this might be important? Well, the code we're about to go through now isn't something I took directly from my work, but it does get closer to simulating a time where it's maybe important to understand these principles. What I essentially did is create 3 functions that do the same thing. There's this value called iterations, and what we're essentially doing is starting at 0, and until we get to 500 million, add the new value to the total. So we'll say 0 plus 1 plus 2, all the way up until 499,999,000, whatever. You get the picture. And that takes a little bit of time. So let's look at that synchronously. Synchronous clicked. Good idea when things are fast enough that they won't block other things. And that took 6.53 seconds. Then we have async. I'm calling this the dumb async. It's a good idea when you need to do something that takes time, but you don't want to block the initial render. And that took a little bit more time, but not a whole lot, especially considering how many calculations are being done. It is important though that this is getting the same value. It's doing the same thing. Now let's look at smart async. All right, so I just actually found a bug in the smart async code that I quickly fixed, but the point is these are all getting the same value and taking roughly the same amount of time, but they have different implications. That being, when I click this synchronous button and I click just say hi, which is all it wants to do is log hello, nothing happens. But as soon as the synchronous call finishes, then it triggers this just saying hi button. So if I click this a bunch of times, it's going to say hi every time. But while the stack is calculating values, no new events can be handled. So let's look at the code to understand what's going on under the hood so that we can better understand these functions. When the synchronous button is clicked, we are logging out what we see. We're then creating a start date, which is marking the start time to the millisecond and setting the total to 0. Then we're going to iterate and do for I iterations, and each I, we're going to add I to the total. And just for context, iterate and do just says, let I equal 0 while I is less than X, I plus plus, and do whatever you're told, passing in that value I. We also have this function milliseconds to second string, and that just prints it out nicely. So synchronously, we run iterate and do to go through all of that, and then print out the total, as well as the amount of time it took, which we calculate by getting a new date, which means the current time when we're logging and subtracting that from start. We're saying right now minus back then, and the difference is going to be the number of milliseconds it took to get until now. Async button, we're actually doing the same thing, but we're creating a set timeout, which is why while async is running, it's still blocking everything. It's still a synchronous call, but we're essentially giving the browser the option. We're basically saying if any message is already up in line, put it after that. So this actually is something that maybe would be a little more valuable if you're calling it in the main loop and you don't want to block a bunch of stuff that's going on. You just want to say, okay, let everything render and then make this calculation. Finally, we have the smart async button, and this code might be a little bit funky to you, so don't worry about it too much. But conceptually what's happening is we're breaking up those calculations into pieces. We're creating a calc async recursively function that's taking in the total number of iterations, the total value count so far, but if we call it right away, it's going to default to 0, and then an I value that also defaults to 0. We're also using this count by value, which is saying essentially that we need to count 10 million iterations at a time. So the first thing we're doing is we're figuring out what we need to count until. So when you run it at the start, it will be 0 through 1 less than 10 million. The next time it gets to here, we will be starting at 10 million and running to 1 less than 20 million. And then for that, figure out this total plus I. It's also worth noting what this code here does is say if I plus the count by value is greater than the total number of iterations that we want to do, then don't overshoot our estimation. Just say only go until iterations. But if I is less than that, then set it to I plus count by, then run this for loop that the other buttons are doing. And again, if your I is now less than iterations at the end of that, call the async recursively, now passing in the updated total and the updated I with the same iterations, because your goal is still to calculate off of the same iterations. Else, log your total and your time, which is again taken from the start time and our current time. And as a result, if I click this smart async, while that's calculating, I can say hi, and it doesn't impact our calculation. Now, if I run start async and then this synchronous one, the synchronous is going to prevent current messages from the smart async from running because they're called one after another. So that would actually slow down our smart asynchronous function. Essentially, the smart async function is saying, don't let me take precedent over anything else that's more important. Now, the final way that we can see the power of this is by this count to 10 function, where if you click it, it just counts to 10, 2, 3, 4, and so on. After it gets to 10, it's all done. So what happens if we run the synchronous during the count to 10? Well, count to 10, run synchronous, and now the counting is actually blocked from being run until after the synchronous finishes. We see the same exact thing with the synchronous function because, as we discussed earlier, all it's doing is creating a message in the stack, but it's not like 10 different messages are in the stack waiting to log 1, 2, 3. And that's because if we look at the implementation of this event listener for counting, we're using set interval, which leaves a reference to the current interval and starts counting to 10, log I, add 1 to I. If it equals 10, then say all done. Otherwise, you've already incremented I, don't do anything, and in another 1 second, another event will be generated. And that means only one event is going to be in the queue. But let's run this a final time and now say smart async. Well, you're allowed to continue counting, get the value from the smart async. And so it gives you this ability to not let one thing block everything else. It breaks up the workload and it allows for a much smoother experience. And if there's anything that will annoy the hell out of visitors to a website, it's clicking on something, being annoyed, trying to click on other things, and nothing's clicking. And then when that finally stops, all of a sudden you've got a bunch of random shit going on that you didn't actually intend to happen, which is exactly why it's so important to understand maybe where bottlenecks in your coding process are going to lead to those types of issues. So a few final thoughts. Understanding the event loop is a precursor to fully understanding asynchronous programming in JavaScript. If you understand what we covered here, then you're ready to have a more grounded understanding in promises, Ajax calls, and things like that. I also want to note that this smart async function that we looked at here isn't an everyday occurrence. Just because most of the time in JavaScript, you're handling simple DOM manipulation, nothing's actually taking too long. And if something does take long, you're most likely going to send it to the server, have the server calculate it, which won't block your call stack or your queue or anything. And then when it's done, it'll give you that answer back and you'll handle it. So again, yes, it was a fringe case, but I hope it helped you understand the importance of at least knowing when async can be helpful. As always, if you found the information on this video helpful in any way, feel free to give it a like, subscribe, comment. All of those things will help grow the channel. Thanks, guys. See you next time.